let's get started. EE210 is called Microelectronics 1, and microelectronics is a very large field, and within microelectronics, as we'll just see, there are sub-branches. This particular course deals specifically with analog circuits. Okay, so in your previous exposure to electronics, you must have heard that circuits can be classified into analog and digital, two broad classes. And this particular course focuses on analog circuits. Now, it turns out that analog circuits also is a very large field. And so in this particular course, what we'll do is focus on amplifiers. So the whole course revolves around amplifiers. The bulk of the course that you see here are amplifiers here. And the amplifiers that are there, the complex amplifiers, they're usually made up of a number of building blocks. So most of our stress would be on the different building blocks of the amplifiers. We'll learn how to analyze those different building blocks. We'll learn how to design them. And then towards the end of the course, we'll take these building blocks, different building blocks which are there, put them together and make a operational amplifier. So at the end of the course, all of you should be in a position to analyze and design basic amplifier blocks, put them together to realize a operational amplifier. The course deals with, as all of you know, that there are two major classes of semiconductor devices. One is the bipolar and the other one is MOS. Most of the circuits, both analog as well as digital, are implemented in MOS. If you go back in history, all of you know that the modern electronics started with the invention of the transistor. It was a bipolar transistor. So the early circuits, early integrated circuits were all bipolar. But then in late 60s and 1970s, MOS came into being, and MOS has several advantages, which you'll understand later on. And therefore, a shift has been from bipolar to MOS, and most of the circuits right now are MOS based. But there are some cases where bipolar transistors are still used. In this particular course, we'll go side by side. We'll do bipolar circuits and we'll do MOS as well. All right, so that's the outline of what this particular course is going to look like. Now, as you understand that if you have to design and analyze a amplifier consisting of a BJT or a MOS, before doing or analyzing the amplifier blocks, you have to understand the device itself. You have to understand the bipolar transistor. You have to understand the MOS. If you don't understand them well, then you can't use them to make your circuits. You'll have problems in understanding as well as designing. So understanding of a bipolar transistor or a MOS is also essential. But there's a difference. In this particular course, we are basically users of a bipolar transistor or a MOS. We are a user, not a designer of a MOS transistor. So when we look at a transistor, we look at it from the perspective of looking at it from the outside. How does a bipolar transistor behave? In the sense of how does maybe collector current vary with collector emitter voltage? How does if I apply a time dependent voltage, how does the current vary? So we look at it from an external perspective, from the perspective of terminal characteristics. When you go to subsequent courses, there you will go inside the bipolar transistor and you'll see how bipolar transistor actually works and the different properties of bipolar transistor, how they arise. So our focus is, when I talk about here, we'll discuss bipolar, we'll discuss MOS, we'll discuss diodes, but we'll discuss them from an external perspective. Okay, from the perspective of terminal characteristics. All right, so that's the outline of the course. So we'll start with device models very quickly. And as all of you know, if you want to understand a bipolar, you have to understand a PN junction as well, a diode as well. And diode is also an element in many of the circuits. So we'll start with a model for a diode, go on to model for a bipolar transistor, start analyzing and building basic amplifier blocks. Once we understand the basic amplifier building blocks using BJT, then we'll shift to MOS. We'll study the basic building blocks of MOS amplifiers, and as I said, towards the end, put them all together and make an operational amplifier. All right, so that's how this particular course looks like. Before I, start go into the details of each one of these here, very briefly, this is the tentative outline of how the grading will proceed. As all of you know that besides the lectures, we have tutorials every week. And along with tutorials, by now all of you know that typically what would happen is that prior to tutorial, we'll give you a homework assignment. Usually I'll post the homework assignment on Fridays, and tutorials are on Tuesdays. So you're expected to go through the problems. And during the tutorial, as usual, we'll have a very quick problem, which we call mini quiz or whatever, 5 or 10-minute problem, followed by a discussion related to the problems that were given as part of the homework or whatever else doubts that you have. So that's the tutorial. Aside from that, from time to time, we may have very small sort of quiz during the class itself. Okay. So that's, please keep in mind that this is tentative. We may revise this in consultation with you. Okay. So this is around 10%, 2 quizzes, 1 before the midsem, 1 after the midsem. Okay. So 2 quizzes, they'll add up to 20. Midsem is 25 and endsem is 45. Tentative in the sense we may want to reduce it to 40 or whatever. That we'll see later on. Okay. So that's the tentative outline. I can be contacted on this email ID. My office and other telephone numbers are here. Books. I've listed, amplifiers are a very old topic. A number of books have been published, and I've just listed 5 of them here. Here, the first book is by a professor from our department, Professor Alok Datta here, Semiconductor Device and Circuits. These are not in any particular order. I'm not recommending that you go, the first book is the most important and the second and all that. These are just in some random order, okay? So I've just listed 5 of them. I'd like to promote a book from our own institute. So Professor Datta has written a book, but that's Semiconductor Device and Circuits. The book which has been a standard for a long time, generations of students, and I also, when I learned analog circuits, I learned it through this particular book, Analysis and Design of Analog Integrated Circuits by P.R. Gray and Meyer. So earlier there used to be, in my time, there used to be 2 authors, Gray and Meyer, and now there are 2 others. So this is a very well written book, and students all over the world have learned analog circuits. These are 2, P.R. Gray and Meyer. They are professors at University of California, Berkeley. They were one of the pioneers in analog circuits, and very well written book. The other one, in these times, perhaps a more popular book than Gray and Meyer is this one, a book by Cedra and Smith, Microelectronic Circuits. So that's another book that you may want to see. And the 4th one, CMOS Analog Circuit Design, is also a very popular book, but it focuses entirely on CMOS. The previous 3 books, you will find both bipolar as well as MOS amplifiers. The last 2 are primarily MOS. And again, they are very, very popular textbooks that are there here. Now, although I've listed all, 5 of them, and one can easily list another 10, 15 books, I'm not going to follow any of them. In the sense that if you think that, let's say, if you miss a lecture, similar kind of stuff you can find, the answer is no. I'm not going to follow any of them. But at the same time, remember that amplifiers is a very old topic, right? Amplifiers has been around for a long time. So whatever I'm going to say, let's say if I discuss common emitter amplifier, yes, you can find a discussion on common emitter amplifier in all the books. All the books will discuss that. But the perspective with which we will look at common emitter amplifier will be different from what you will find in the books here. Okay. So these are not a substitute for lectures, but reading them would help you gain a deeper knowledge, deeper perspective on. See, each book, each author writes it from his or her own perspective, right? So each book is written from a certain angle, emphasizes certain things, has a different set of examples. So from each book, of course, you can learn new things. So as I said, these are good books. You may want to get hold of any one of them would be fine for this particular course. But our discussion in this particular course would be different, in general different from what is there in this. If you have more time, I know you have a lot of courses and there are many things, but if you have more time, you want to know what is happening in the world of analog circuits, you may want to go and browse these journals. Our library has all these journals, and we have a digital subscription also. So for example, you can just do a search on IEEE Journal of Solid State Circuits, IEEE Transactions on Circuits and Systems. These are all books, these are all journals for which we have subscription. And therefore, if you want to know what is happening now, what are the current topics and what are people working on, if you're curious, you can go to these journals and you can get an idea. In the beginning, of course, if you go and try to read through the journal, you'll find there are many things that you don't understand because you don't have the relevant concepts. Hopefully, by the end of the course, you have much more understanding, and you may be able to appreciate the papers a lot more. Okay? Since this is an undergrad course, so we can't take up papers from the journals and discuss them. We simply don't have time. But in future, especially in graduate courses, you'll get a chance to do that in more detail. I've been teaching this course for a long time. And the last time that I taught was more than 2 years ago. And what I did was, while I was teaching, I recorded all the lectures as well for the benefit of students. So the previous years, lecture notes are all available here. EE210 lecture notes are available at this site. And so lectures at this time would be similar, but there would be differences as well. Okay? So these lectures are all available to you. They are all organized in lecture 1, 2, 3, 4, right down to maybe lecture number 39 or 40 lectures or so. So they're all available here. If you go to this particular site, you'll find E210 lecture 1, E210 lecture 2, E210 lecture 3 and all that. So as a reference, besides the textbooks, you can go through these lecture notes as well. Okay? All right. So lecture schedule is, all of you know. Tutorials are here as well. Tutorials will be organized in 4 sections. I'll send you these slides to you so that you know which section you belong to. Section A, B, C, D, and all that. So you don't need to take it down. I'll send them to you. All right. So as I said, before I go into amplifiers, any complex system, it need not be an engineering system. It can be a social system also. Any complex system you would see is designed or is made up of in a hierarchical manner. So if I look at an analog system, right? Analog system is also hierarchical in nature. And hierarchy can be expressed in this particular manner. One of the ways of expressing hierarchy is this. Let me illustrate so what you see over here is an inverted pyramid. And at the bottom, you see device. Then you see basic circuit blocks. And then you see subsystems. And then you see systems here. Now let me illustrate. Right? Device, example of a device is bipolar. It could be MOS. It could be other devices as well. So besides bipolar and MOS, there are other kinds of devices as well. A basic circuit block, well, one of the basic circuit blocks that you'll read is a differential amplifier. There are many such basic building blocks. Subsystem, well, what you do is you can see why the hierarchy is there. I have a device, let's say bipolar. I take several bipolar transistors, connect them up together along with other elements, and I make a basic circuit block, which is a differential amplifier. I take many such basic circuit blocks. Differential amplifier is one. There's a gain stage. There is an output stage. There are many stages. We put them all together and we make a subsystem. An example of a subsystem is an op-amp. Then we take op-amps and we take oscillators and we take other blocks and put them all together to make an analog system. This is a automatic blood pressure meter. So it's made up of amplifiers, comparators, A to D, D to A, and all kinds of things that are there here. Those are all subsystems here. So when you look at a complex system, like a blood pressure meter, let's say, what you can take a blood pressure meter, and it's a complex system, you can decompose it. Decompose it into what? A series of subsystems. Example of a subsystem is an op-amp. And if you take a subsystem, you can again decompose it, and what would you find? It's made up of series of building blocks. And if you take a building block and you decompose it, what do you find is made up of bipolar transistors, resistors, capacitors, and things like that. Okay. So, this hierarchy makes it easier to understand. What you realize is that, in fact, using a few basic building blocks, you can construct a wide variety of subsystems. In this particular course, we'll only look at op-amp using basic building blocks. But using those basic building blocks, you can make comparators, you can make multipliers, you can make many, many other things. All right. So many, many subsystems that are there. And once you have these subsystems, then you can make a variety of actual systems. So you're getting into the product stage where you have a blood pressure meter. Okay. So that's how, if you want to understand how microelectronics is organized in this inverted pyramid fashion. Okay. So the whole of microelectronics, you can see it here. Microelectronics, a part of microelectronics is what? Devices. Study of devices. A part of microelectronics is what? Study of basic circuit blocks. It could be basic analog circuit blocks. It could be basic digital circuit blocks. A part of microelectronics is analysis and design of subsystems, larger. We are talking about op-amps, comparators. Maybe we are talking about microprocessors. We are talking about adders, subtractors, all kinds of things. These are the subsystems here. And then, of course, putting them all together. Maybe an entire computer. This is a simpler example, a blood pressure meter, or maybe a system for MRI, for doing magnetic resonance imaging. There's a whole electronic system which is involved in carrying out the imaging. So that entire system is a part here. So if you look at it, if you look at our curriculum, of course, wants to cover all aspects of microelectronics. And you can see here, at the device level, the key course which will cover devices is 311, which is next semester. If you want to understand semiconductor devices in detail, you want to go inside a bipolar transistor, go inside a MOSFET, understand how a MOSFET works, what limits the MOSFET, and all the other details, this is the course, 311. And if you want to understand it even more, if you want to go into further depth, then there are a series of other courses here at the device level. We have 614 and 616 and 611. And, as you go through your stay here, you'll find what these courses are all about. So we have a set of courses which address the microelectronics at the device level. Then we have a set of courses which address microelectronics at the basic circuit blocks. EE210 is one example, which deals with circuit blocks of analog systems here. EE610 is an advanced level of EE210 here. And 370 is another course that you'll do next year, which deals with digital building blocks. Okay, so that covers the here. At the subsystem level, these courses that I've listed here, they also cover things at the subsystem level here. EE210, as I said, will look at op-amps towards the end of the course. EE610 does a more detailed analysis of op-amps and other blocks. In E370 also, we go beyond the basic gates and counters and all of that, and we look into data paths and controllers and microprocessors and all of that here. So these courses cover the subsystems level. At the systems level, this is what, in brief, this is what you find microelectronics is in a simplified form. Does everybody understand why is it an inverted pyramid? Why didn't I make it a rectangular block? Why a pyramid? Huh? More complicated, yes. Part of the answer. Why an inverted pyramid? Because, the reason why I put is, how many devices do we have? How many devices do we have? Very few, right? The devices that you're familiar with is a bipolar or a MOS. A handful of devices. Unique, in terms of unique devices. A bipolar or a MOS or a diode. We have very few devices. But with those very few devices, how many basic circuit blocks can we make? Many, many. And with those basic circuit blocks, when we add them up, how many subsystems can we make? Huge number. And with those subsystems, how many systems can we make? A wide variety. So it's an inverted pyramid for that reason. That with this very few devices, you can make a large number of circuit blocks. With these circuit blocks, you can make even larger number of subsystems and even larger number of systems that you can construct here. So that's why it's an inverted pyramid. All right. So what is microelectronics then? How would you describe? Say a friend of yours asks you, what is microelectronics? A friend from civil engineering. So you're doing a course on microelectronics, right? So they say, what is this microelectronics all about? I mean, you can't give an entire lecture. You have to explain in a sentence or two or three. So if I am asked, one of the ways that I like to say, what is microelectronics? Well, it's a field which deals with implementation of ideas on a piece of semiconductor. Whatever idea you have, you see, you may have a friend who's in signal processing, who's interested in signal processing, right? Whatever ideas you have as electrical engineers, eventually for that idea to become actionable, to become active, to bring it to life, it has to be implemented on a piece of semiconductor. It can be a complex algorithm which plays chess and can beat the chess champion. But that complex algorithm has to run. The algorithm has to be stored in a memory. And memory is what? A piece of silicon, made up of silicon. The algorithm has to run on a processor. And the processor is again made of transistors and all that, which is again of silicon. So all the complex ideas that you see, eventually for them to work, they have to be implemented on a piece of semiconductor. And the most dominant semiconductor, as all of you know, is silicon. So what is microelectronics? If you want to be poetic, you can say it's writing in sand. Right? So everything that all the ideas that you have, it has to be finally etched into silicon. And silicon, as all of you know, is derived from sand. A particular kind of sand, not any sand, but a particular kind of sand. Right? So this is a field where we learn how to transform ideas and implement them on a piece of silicon. Okay? A piece of semiconductor. All right. So let's now come down to our course. So it's a course on amplifiers. And one of the ways in which we describe an amplifier is by a block like this. We draw a triangular block, and this is the input side here, and this is the output here. And the amplifier, as all of you know, the purpose of an amplifier is to take a weak signal and transform it into a stronger signal here, while preserving the shape. Whatever is the shape of the signal here, the shape has to be preserved, and you have to increase the strength of the signal here. And how do we describe the strength of the signal? We say that the power output, the output power here, divided by the signal power that goes in, has to be greater than 1. So this is the essential condition for a block to be called an amplifier. Output power divided by signal power is larger than 1. Now, of course, you're getting much more power than the input. This is only part of the story, right? It doesn't violate law of conservation of energy. How can you get more power as compared to the input power? That's where the supplies are, right? So what you're doing is you're taking power from the supplies here and transforming that power. So it's a DC voltage that is there. You're taking power from a DC supply and transforming it into an output power. And how do you carry out the transformation? Depending on the signal that is present here. All right. So that's the essential condition for making an amplifier. I've written it in a more general form. X could be voltage or current. Y can also be voltage and current. So you get different kinds of amplifiers, which we'll come to in a minute here. Now, I want to make a strong statement about if you're thinking, well, amplifiers are, why are we devoting an entire course to an amplifier? Aren't there more interesting things? There are a lot of other things besides amplifiers. Why are we not discussing those other things as well? And I want to make a very strong statement here. And the statement is that amplification is the heartbeat of electronics. In what sense? As all of you know, that if the heartbeat ceases, the life ceases, right? And I'm making a strong statement that if amplification, if at any point, anywhere, if amplification ceases, the whole of electronics would cease. None of the electronics that you're familiar with will work if you don't get amplification. you would appreciate that a little later on, not right now. You may be wondering, I've done an inverter, right? In ESC201, I've done an inverter or a NOR gate. Where was amplification there? What did a NOR gate do? Took two inputs and did some logical operation on that, right? Where was amplification there? But I'm claiming, if there's no amplification in a NOR gate will not work. At the heart of, again, in a NOR gate will not work properly if there were no amplification. None of your basic gates will work without amplification. Your adders, subtractors, microprocessors, whatever you take it, none of them will work if there is no amplification. Amplification is very, very basic. It's an essential condition for electronics. And if amplification were to stop for whatever reason, if let's say tomorrow for whatever reason, let's say your bipolar or a MOS transistor cannot amplify, the whole of electronics would cease. Nothing will work. So it's for that reason, because of its importance, amplification is so important that this entire course is devoted to amplifiers itself. Now, maybe I can make an even stronger statement than this. Amplification is the heartbeat of electronics, fine. By the way, there's another part of this particular course here. There's a nice poem whose first line I really like. There's a poem you can go and read by William Blake, and some of you may have heard these lines. These are very, very famous lines, right? To see a world in a grain of sand and a flower and all that here. The first line here, to see a world in a grain of sand, is very pertinent for us. Why? Why is it so important for us? To see a world in a grain of sand? I mean, we're talking about microelectronics. So when you think of sand, it's connecting with microelectronics, right? So what I want to say is that even, all these courses that you go through, we are going through a course on amplifiers. But you can see the whole world of analog circuits. The whole world of what happens when an analog designer, let's say, is sitting in an analog device company or Intel or whatever he's doing, whatever is happening in the world of analog systems, you can appreciate through what we are doing in this particular course, through our discussion on amplifiers. That's what this particular line is. You can see a whole world in a grain of sand. You can see the whole world of analog circuits through this particular course here. If you're interested in knowing what happens in analog circuits, what do they do? How do they go about designing? With the right perspective, you can see all of that through this particular course. Okay? And this guy, he writes it nicely, that if the doors of perception were cleansed, everything would appear to man as it is infinite. But he's, of course, being very philosophical, infinite and all that. But what I'm saying is not only analog circuits, but you can see the whole, with the right perspective, you can see the whole of electronics. What this whole electronics is all about through this particular course. Okay? And so many times, you may wonder, and it's true that many of the things that you learn in a course, I mean, how many of you will actually, let's say if I discuss common emitter amplifier, 10 years down the line, how many of you would be even, thinking about common emitter amplifier? I can say none. Probably none. Any of the things that we discuss in this particular course, probably in a direct way, one or two or three may be using it at all. So the issue is, what do you carry away from this particular course? If you're not going to use it 7 years, 10 years from now, what do you carry away? Why should you even study? But what I'm saying is, besides the details that we study here, we'll study details and all that, there are larger themes. Larger themes. For example, when I talk about design of a common emitter amplifier, if you look at it in a proper way, I'm talking about design of any engineering system. And why engineering system? Design of any system. And in any system, then, how do I approach design? What are the issues? So, when you take it, what we are doing here, maybe not in a direct way, you would be using it several years from now and all that, but in an indirect way, many of the concepts, the method of analysis, the method of design, they prove to be very useful. You'll find them of importance here. Okay? let me make even more stronger statement about amplification. Let me say the foundation of civilization is amplification. The first I said, the amplification is the heartbeat of electronics. Some of you may be wondering, really? Is it that important? Now I'm making a stronger statement. Amplification, the foundation of civilization is amplification. You agree or not? The foundation of civilization. Now I'm not talking about electrical amplification. I'm talking about, look at this, amplification in quote. Amplification. The foundation of civilization is amplification. Well, let me look at this. Is this an amplifier? A few grains of wheat, when planted, what do they do? 1 grain of wheat will result in maybe 100 or 1,000 grains of wheat. Right? You plant one and you get 100 or 1,000. Right? And how does it occur? Well, you have something which is weak and you get something which is more. But there is more, analogies will of course break beyond a point. So don't stretch it too far. But look at this here. Look at how does this, from one you get many? Well, you harness the power of the sun. The solar energy is used, right? Along with water and other things. The energy of the sun is used to carry out this transformation from one to many. In the same way, the energy from the battery, we take battery and we take the energy from there and we use it to transform something which is very weak into something which is very strong. I mean, you go and talk to economists, all of you must have heard productivity. Productivity is at the heart of all of economics, all of progress and all that. Productivity means what? If you think about it. Productivity, if you think it in a very general sense, is amplification. Is that you are able to do more. In a certain amount of time, you're able to do more. Anyway, you think about it, I'm making a strong statement that foundation of civilization is itself amplification. If amplification, you talk to economists, if they say productivity, if productivity doesn't increase, economy will stagnate, all kinds of problems in that. Okay, if there were no increase in productivity, we would have probably never gone from hunter-gatherer to more civilized society at all. Okay, so think about it. The foundation of civilization is amplification, so amplification is very, very important. Let's come down to earth and talk about our little amplifier here. So as I said, amplifier, there's an input, there's an output here. Input can be voltage or current, and the output can also obviously be voltage or current. And therefore, depending on our interest, now remember, when I apply a voltage at this point, there would obviously be a current also going in. Right? So both of them are always present. When I look at the output, when I have a voltage, I will have a current as well. I mean, I won't be interested in output voltage and there is no load connected, then what am I doing? Right? If there is no load. So voltages and currents are obviously present at the input. Voltages and currents are obviously present at the output. It's our interest which defines what kind of an amplifier is it. I'm interested in output voltage rather than current. For me, let's say the output voltage is more important and input voltage is more important, the way my amplifier is organized. So what is more important is output voltage and input voltage, and such an amplifier, we call it as a voltage amplifier. I'm designing that particular amplifier with the perspective that the input is in the form of a voltage. I give more importance to voltage here, and similarly give more importance to the output voltage here. So we call such an amplifier where our prime interest is in the ratio of the output voltage and the input voltage. We call this an amplifier as voltage amplifier. Where our prime interest is in the ratio of output current and input voltage, that ratio is more important for us. We call this as a transconductance amplifier. And similarly, when our interest is in the ratios of the two currents, we call such an amplifier current amplifier. And then, of course, the other thing, which is transresistance amplifier. So each one of them is important. There are applications where one is interested in a transconductance amplifier. There are applications where one is interested in a current. But as the most popular, the places where we use amplifiers the most is where our interest is in the ratio of the two voltages. ratio of output voltage and input voltage itself. And we call such amplifiers as voltage amplifiers here. So although there are all these different varieties of amplifiers, their design is different because the emphasis is different, and therefore the design becomes different. We would spend most of our time on voltage amplifiers. Where output voltage is important for us, and we would like to, in general, obtain a large voltage amplification. Okay. So ideal voltage amplifier is, so now my interest is in voltage, so I put in here input voltage, and the interest is again output voltage here. So I'm interested in voltage gain. And an ideal amplifier is where V0 is AV times Vin. AV is the voltage gain. But it's important, this part is very important. AV is a constant. AV is a constant. That's why I'm calling it an ideal voltage amplifier. This has to be, for an ideal voltage amplifier, this is a linear relationship. Otherwise, note that if AV were to depend on Vin, then what would happen? Relationship between V0 and Vin would become nonlinear. Nonlinear means the output will not be a replica of the input. One of the conditions for amplification is you should make the output signal stronger, but not distort it. It should be a faithful reproduction of what the input is. You're not supposed to distort it. Keep it as it is and make it stronger. And for that to occur, you have to have AV, which is independent of, let's say, input voltage here. But in general, this is ideal. But in general, by the way, should AV be larger than 1 for me to call it a voltage amplifier? For me to call it an amplifier? Should AV be greater than 1 if I would like to call something as an amplifier? Yes or no? You should not forget the definition of amplifier is output power should be greater than input power. No matter whether it's a voltage amplifier, current amplifier, transresistance amplifier, or whatever, this is the essential condition. Look at this. What is this? Transformer, right? Transformer, I can get V0 greater than Vin. Can I call it a voltage amplifier? V0 is larger than Vin, right? V0 by Vin, I can get 10, 100. Huh? Why? So that's the important point. When do you call something an amplifier? It's not simply the output ratio of output voltage and input voltage is higher than 1. You can only call something an amplifier is if besides, fine, you get output power more than input power. Then only you can call it an amplifier. Otherwise, you can't call whatever device it is as an amplifier here. So that's essential. Because soon, in this particular course, we'll see a common collector amplifier. And in common collector amplifier, in fact, V0 is less than input voltage. It's an amplifier where voltage gain is less than 1. But we still call it an amplifier. Why? Because there's a power gain. Output voltage is less than the input voltage, but there is a power gain, and it's a very, very useful amplifier stage here, common collector amplifier. So never forget that to call something an amplifier, this condition has to be met. Output power divided by input power has to be greater than 1. Okay? That's an essential condition. So, ideal amplifier is, coming back to voltage amplifier, V0 is AV times Vin. But in practice, what you will find is that this gain that you see here is not just a constant. Gain depends on many things. Gain depends on frequency. Now, gain, which means that gain at certain frequency is so much, gain at certain other frequency is something else. So that's a non-ideality. Ideally, I would expect my amplifier to have a constant gain. It should amplify all frequencies equally. If you imagine that the signal has, let's say, 2 frequencies, 1 kilohertz and 10 kilohertz. If the gain at 1 kilohertz is 100, and if the gain at 10 kilohertz is 75, what would happen to the output? Will it be an exact replica of the input? No. You have emphasized one frequency over the other. In some sense, you're causing a distortion. Right? So you don't want the gain to be a function of frequency. You want gain to be independent of frequency. But all amplifiers have a dependence of gain on frequency. The other thing is all amplifiers will depend on the input voltage that you applied. If you apply a smaller input voltage, you get one gain. If you apply some different input voltage, you get slightly different gain. So you find that the gain of the amplifier is a function of frequency, is a function of input voltage, is a function of how much load resistance you attach here. You know, if I have an amplifier and if I attach 1 kilo ohm load, I get a gain of 100. If I attach a 50 ohm load, maybe I get a gain of only 10. So the gain that I get from my amplifier depends on how much load I attach, RL here. The gain that I get depends on how much source resistance is there. The gain that I get, you know, in fact, almost everything depends on temperature. You measure gain in summer and you measure gain in winter, your gain may be different. It's temperature dependent. So what you get is you find V0 is AV times Vin, but AV depends on many other things. Depends on frequency, depends on input voltage, depends on RL, RS, T, many other things. And, you know, even when you don't apply an input voltage, you get something at the output, noise. The amplifier adds noise. The elements that are there inside your amplifier, what are the elements inside an amplifier? A resistor, a transistor, they all add noise. They are all noisy. So when your signal comes in, right, the signal comes in, even if it's a pure signal, if the signal comes in and you amplify it, what the amplifier will do is, in addition to the amplified output, it will add noise to it, a random signal to it. That is always there. So this, this noise that is there here. When I think of amplifiers, what is important? Well, you may be thinking, if I'm talking about voltage amplifiers, the only thing which is important is how much is the voltage gain? That's not true now. We have to talk about, voltage gain is there. We have to talk about how does your amplifier behave with respect to frequency? How does your amplifier behave with respect to the magnitude of the input voltage? How does your amplifier behave with respect to RL and RS? How much noise is there? So we see that in an amplifier, it's not just the voltage gain. There are many other parameters of amplifiers which are important, which tell us about these dependencies here. This F and Vin and RL and RS and all that. So what we have to do is understand that what are the important parameters of an amplifier. If it were an ideal amplifier, all you need to do is say the gain of this particular amplifier is 100, and that's the end of the story. But because it is non-ideal, I have to specify the non-idealities. We have to have a measure of the non-idealities which are there. And that's the only way then you can specify. For example, if I look at my amplifier's dependence on frequency, let's look at this one. Many amplifiers have voltage gain which varies with frequency in this particular manner. We have plotted this on a log scale, 20 log 10 AV. What you find is that the gain falls at very low frequencies and the gain falls at very high frequencies. And the gain is constant in between. That's a typical dependence of gain on frequency. Large variety of amplifiers will have this kind of a dependency. Now, where do you think your amplifier is ideal? We said ideal amplifier is what? It should not depend on frequency. So you can think of your amplifier as ideal over this range here, right? In this range, gain is not dependent on frequency. But when you go to very low frequencies, gain becomes dependent on frequency. When you go to high frequencies, gain again becomes dependent on frequency. So when I talk about gain of an amplifier, when somebody says, well, this amplifier has a gain of 50 or 100, what are they talking about? This gain, this region, gain in this flat region here. They're talking about this particular region. And what do we call this region? Mid-frequency region. Obviously, it makes sense. At lower frequency, gain is changing. At higher frequency also is changing. There's a mid-frequency range where gain is relatively constant with frequency here. So when I talk about gain 100, 200 or whatever, I'm talking about gain in this region. So whenever we talk about gain now, please understand, even if it is not said, it is the mid-frequency gain. Mid-frequency gain here. Besides now mid-frequency gain, what else do you think is important for an amplifier? What are the other important factors now from this diagram that you can see? Is this important? FL and FH. What does FL tell you? FL is the point where the gain has fallen by 3 dB, 1 by root 2 of its value here. What does it tell you? FL tells you that if you are above FL, then you're okay. Gain is relatively flat. But as you go below FL, gain is a function of frequency here. So it's telling you is the lower frequency range up to which maybe you can use your amplifier. Don't go lower than FL. Then you are in trouble because gain is a function of frequency. Also, it tells us don't go over FH. Gain again becomes a function of frequency and starts dropping here. So besides the mid-frequency gain, what are the two other important parameters that we know of an amplifier now? FL and FH. Sometimes people, what they do is they take FH minus FL and they call it the bandwidth of the amplifier. So this is the bandwidth over which your amplifier would work fine. Its gain would be independent of frequency. If you go beyond that, gain would be frequency dependent and gain would start falling. So besides the mid-frequency gain, we've identified two other parameters, FL or FH, lower cutoff frequency and upper cutoff frequency, or a difference of the two, which is the bandwidth. So bandwidth of an amplifier is another very, very important parameter besides the mid-frequency gain. Okay, bandwidth here. Some amplifiers actually don't have characteristics like this. They have characteristics in this particular manner. In the sense that they can amplify, their gain does not drop as you go to lower and lower frequencies. In fact, they can amplify a DC signal as well. Okay, so they don't have a lower cutoff frequency. They can amplify right from DC and then to some higher frequencies here. But all amplifiers have this part here. The gain will start dropping at higher frequencies. Okay, why it would drop, we'll see later on when we discuss amplifiers. Such amplifiers, we call them DC amplifiers, not because they can amplify only DC. As you can see here, they can amplify DC and they can amplify other frequencies as well. But just to emphasize the point that they can amplify DC signal also, we call them DC amplifiers. In contrast to amplifiers like this here. You know, when I go to lower and lower frequencies, the gain becomes negligible. They won't amplify a DC signal. While these would amplify a DC signal as well. Op-amp is an example. Op-amp would amplify DC signals. Okay? Now, as I said, if you look at an amplifier like this, the gain falls as a function of frequency. Eventually, if you keep on increasing frequency, a stage will come where the gain, note that this is 20 log AV, where the gain becomes 0 dB. In log scale, it becomes 0, which means in a normal scale, gain becomes equal to 1. So a frequency at which the gain of an amplifier becomes 1, obviously we call such a frequency as unity gain frequency. So we are seeing a couple of parameters that are representative of how an amplifier performs in the frequency domain. We can say lower cutoff frequency or upper cutoff frequency. We can talk about bandwidth, or we can talk about a frequency which is the unity gain frequency where gain falls to 1. Next lecture we'll look at, so this is in the frequency domain. Well, you can look at an amplifier in the, in time domain. What happens, how does an amplifier behave in the time domain here?